Okay, hello. Just in case you don't know who Breaker is, it's a startup company based in Silicon Valley, San Jose. Breaker just focus on SoC verification solutions. And I will introduce you to our main tool, TrekSoC, but I will a little bit more deep dive on how you could close your coverage with graph-based scenario models. So we believe SoC verification has a big problem because we can't just apply random constraint methodologies like UVM to the full SoC verification. And I give you just two reasons here. For example, long random simulations are just not applicable to SoCs. And it would take a long time to close your functional coverage loop with a constrained random-based methodology. Basically, you run your long test overnight, in the morning, look at if you hit your functional coverage targets, and then maybe reapply some constraints and try again. This just doesn't work for SoCs. Also, UVM or other methodologies don't provide you with a link between the test bench and the embedded processor. By that I mean, usually we have a C program running on the embedded processor, some external components, and it is difficult to synchronize them. So what people tend to do is they write C tests for the embedded processor to verify the SoC. This is possible for small SoCs, single core, a few peripherals, but as soon as we talk about multi-processor, multi-threaded applications, it is very difficult to write these tests, and it's also extremely difficult to maintain these tests. So typically what people see is they wrote maybe 1,000 C tests to verify the SoC, they get a new derivative, and they'll probably have to touch all the C tests again to make them work on the new derivative. This is a big loss in productivity. Another problems are the weak verification metrics. So I guess most SoC teams rely on interface toggle coverage. That's what they do. There's no means of functional coverage other than your handwritten C test. So today's reality, SoC teams really switch and ship. So they run some checks to verify that the blocks are hooked up correctly. Maybe they reuse some of the UVM components on the SoC level to, for example, at the cluster level, verify a bridge or a switch, something like that. And then they do write some basic C tests to make sure that the IPs can talk to each other. Again, there's, other than doing toggle coverage, and maybe if they're a little bit more sophisticated, doing some stucket fault injection on the interface, there's no means to measure how good we are. So I guess because people are aware that they have a problem on the SoC verification, they rely on emulation and prototyping. But this has some downsides as well, because if you find a bug in emulation, prototyping, or even post-silicon, they are a lot harder to diagnose and fix, and they also tend to delay your project cycle. Also, one other problem is that if you run production software on your emulator, this software is typically well behaved. It doesn't expose corner case problems usually. So let me introduce to what we call the SoC verification Iceberg. So today we have visibility into connectivity and IP integration tests. That's what we do, that's what we see. But there is a lot more to test on multi-core SoC designs. Like we got to do some system use cases. We have to address concurrency, memory coherency. On top of the system power management, we talked a little bit about this today, and also some performance verification. And the bugs hidden here under the water, they don't remain forever. They don't remain hidden forever. And the last thing we want is that they surface at the customer. So we believe, as Brecker, we believe that having C-tests executed, loading into the memory and executed by the embedded CPU is a great way to verify your SoC. What we don't believe is that a human should do this. Because a human can only address what we said, connectivity tests and IP integration tests, when it comes to writing multi-core C tests to address concurrency and coherency and overlay this with system power management scenarios. A human can just not comprehend this. So what we have a solution is called TrekSoC. TrekSoC takes in higher level models like your register memory map. So for example, we read your IP exact description and generate a register model. You also would write driver scenarios. What we understand about driver scenarios is that these are the scenarios who move the data of a single IP. Let's say you have a UART or an SPI or USB. This is the scenario who tells the tool how to move the data. On top of that, we layer application scenarios. Basically, application scenarios you could imagine is like taking a UART and the DMA and chaining them together. And on top of this, also system scenarios like power management. So what we do is we're raising the abstraction level and synthesize C-tests for you. And also, since we know about when things should happen, we will synchronize the C program running on your embedded CPU with your external drivers, like in UVM, I believe they're called drivers. Previously, we talked about BFMs. This allows you to, because you're working on a much higher abstraction level, this allows you to stress your system much more than you could ever do with a handwritten C-test. Those scenario models basically consist of graphs. And I have some later slides talking a little bit more about graphs. The great thing about graphs is that you can easily connect them to each other. So let's assume you have your scenario models. You can generate your C-tests, but what you can also do is you can, instead of having a CPU in your SoC interpreting the C code, you can replace the CPU with BFM. We usually call this the headless mode. And you can also reuse single scenarios on the IP level. What's not shown on this slide, the C-test obviously could be run also on the emulator or post-silicon. So we have a seamless reuse chain of these scenario models. So this is a small example of a graph, and we model our scenario models with graphs. And graphs allow us to visualize the verification space. Our customers really tell us once they get used to drawing a graph, they don't want to do anything else anymore. They really love it because it helps them to think through the pair verification space. They don't have to learn a lot of things like going for all the UVM training classes. Usually after maybe a few hours on the whiteboard, they understand how they have to design the graphs. And the beauty about the graphs is one path through the graph or multiple paths to the graph are essentially a test case. So now you can imagine that, okay, there are illegal paths through my graph. I have to constrain those graphs, like I would constrain also my UVM test bench. What often happens is that people tend to over-constrain their test bench. The same could happen here. But what's possible with TrekSoC is you can do a pre-simulation reachability analysis, which means the tool tells you pre-simulation which nodes or paths you cannot hit. So rather than finding this out after you ran your simulation and don't hit your coverage points, the tool will tell you in advance that you can't reach them. So you can change your constraint and do the reachability analysis again until you're satisfied. The tool allows you also to visualize the coverage. In this case, you see that some of the nodes are red. This means we have not visited those nodes during our simulation. If you have this case, you can ask the tool to actually cross some nodes. Here, for example, we have a set of 4 nodes and a set of 2 nodes. You can ask the tool to cross these nodes, which means you need a minimum of 8 paths you have to walk to create this interesting scenario. If the tool does that, it still randomizes all the other decisions inside the graph, which means you're not creating really a directed test. It's still a random test, but a very dedicated random test to hit your functional coverage requirements. This allows you to very quickly close your functional requirements / your test plan. So in essence, you don't have to go over simulation, do long loop cycles to reach your functional coverage goals. So in summary, stitch-and-chip verification is not sufficient anymore for SoC. TrekSoC raises the abstraction level and automatically generates self-checking C-tests. Those tests run on an embedded processor and link automatically to the test bench. So the synchronization aspect is taken care for you. You can quickly satisfy your functional coverage requirements, basically meeting your test plan, but you can still generate deep corner case scenarios because it still provides you with the full power of random verification. Scenario models are easy and natural to create. So again, the learning curve to create those scenarios is very, very flat. It's not as steep. You don't need C++ or system Verilog heroes to do this. Graphs very efficiently and capture the verification knowledge. Obviously, they also visualize the verification space very nicely. And because you can visualize the verification space, it helps with internal communication. And guess what? Once you basically have a graph, lots of people use this graph as the verification plan together with the coverage requirements. Thank you very much. And
there's one question. Any more? Okay.
Yeah, just a quick question. I was wondering how complex the various register maps and memory maps can be, or whether it's just this is just a connectivity test, or whether the individual interfaces that you're modeling can be more complicated.
Okay. So obviously we support the whatever is defined in the IPXX standard. By reading the information, we also can automatically generate a register test. This is a no-brainer. However, the register models we create, you can also reuse them in order to finally access the register from the driver scenarios. The same is true for the memory map. Yes. Very good question. Okay, the question is, what's inside the bubble? For SoC verification, the bubbles can be pretty abstract. So what we do when we start from the top, we create pretty sparse models, scenario models. They usually, for example, call a software driver you already written. Let's say you have a UART, which you have to put into a certain mode to do a transfer. This might be inside the bubble. If you have IP verification graphs, then usually the bubble is, for example, a register access. And all the decisions before are, for example, the IP can be operated in a master or slave mode. So what you have is a purple diamond to make the decision, should the IP be in master and slave mode or slave mode. Does that answer the question? So you basically, it can be any level of abstraction inside the bubbles. I'm not sure. That depends. If you don't have software drivers, you would use the register interface. And malloc, alloc we provide for the memories. If you do have those drivers already written, you would not reinvent this. You would obviously use those drivers.
You said when you have a C-based directed random test methodology, usually on the SoC level, you have to redo all the tests. That's a true statement. It's our experience that this is caused by the huge amount of parameterization that is possible in the RTL. So no SoC has the same IP. It has different IPs, flavors because of the parameterization. How you can handle these kind of things.
So what we usually see from derivative to derivative, functionality gets added. Okay, and so what that would mean, you have you have developed your scenario models. You certainly have to add a couple of nodes into the graph, but after generating the C-test, everything will fall into place because you changed the higher level of abstraction rather than going down to the drivers, or basically to the real C code. Well, all the permutations are captured in the graph, aren't they?
I think it might be a good question